Leonhard Euler was born in Basel, Switzerland in 1707. Early on in his life, he established his genius, and his father, recognizing this, was able to work out an arrangement with Johann Bernoulli for young Euler to study mathematics. In this arrangement, Euler would study on his own during the week, and on weekends would have access to Bernoulli for 1 hour. During this time, he would ask him questions on the things that he was unable to work out on his own during the week. One of the reasons that Euler may have been so successful is that he had an excellent memory. It was said later on in his life that he had memorized the first 100 prime numbers, and not only that, but all of their squares, cubes, and fourth, fifth, and sixth powers. Where others needed a calculator to work out difficult problems, Euler was reportedly able to do these things in his head. In 1727, when Euler was just 20 years old, he was appointed to a position at St. Petersburg Academy in Russia. He was able to obtain this position through the influence of Daniel Bernoulli, Johann Bernoulli's son. This appointment was not a mathematics position, but a position in medicine and physiology. However, Euler was just happy to have a position at that time. Finally, in 1733, he was able to obtain the math chair position previously held by Daniel Bernoulli, who had left to go back to Switzerland. It was during this time that Euler began to lose sight in his right eye. He soon became virtually sightless, but continued to work unimpeded. In 1741, Euler left St. Petersburg to take a position at Berlin Academy to work under Frederick the Great. However, due to Frederick's insensitive nature and insulting comments, Euler eventually returned back to St. Petersburg. In 1771, he began to lose vision in his normal eye. He became almost totally blind, but continued to move forward in his work by dictating his equations and formulas to an associate. Euler was able to accomplish much during the years not mentioned in this slide, but we will discuss some of his major accomplishments in the upcoming slides. As one of the most prolific writers of mathematical works, Euler's many important discoveries are beyond the scope of this presentation. On this slide, we will cover two major works by Euler. The first, translated to the Introduction to the Analysis of the Infinite from its Latin form, is perhaps Euler's most well-known work. This work has been compared to Euclid's Elements due to the manner in which Euler organized earlier discoveries and cleaned up proofs. In addition to summarizing prior mathematical works, Euler also added volumes on integral and differential calculus, essentially recording all past and present mathematical discoveries into one comprehensive work. The second, Opera Omnia, which translates to the works or complete works, is 73 volumes of collected papers which contain 886 books and articles written by Euler during his career. These works were on a variety of topics, including engineering, mathematics, mechanics, and astronomy. Euler's legacy is one that will not be easily surpassed. He was and still is one of the most important and prolific mathematicians in history. His collected works fill over 70 large volumes. In addition to the discoveries that bear Euler's name, there are many that do not. Others have been credited with discoveries that were in fact discovered already by Euler and which were present and tucked away in his other works. Euler's work was the first to appear modern to today's readers. However, to quote Dunham, this of course is not because he chose a modern notation, but because his influence was so pervasive that all subsequent mathematicians adopted his style, notation, and format. Euler led the way for mathematics as we know it today. In addition to the mathematical legacy Euler leaves behind, it is interesting to note that unlike many of his predecessors, Euler was known to be kind and generous. He socialized with and cared for others, and this even showed in his work. He didn't only write for the mathematical geniuses of the world, but would write in a more simplistic and understandable way so that his work was accessible to more people. He remained more interested in helping others to understand than attempting to impress them with his superior intellect.
As we saw in last chapter, it had been proven by one of the Bernoulli brothers that the sum of the reciprocals of natural numbers diverges, aka it adds to an infinite quantity. But what if we were trying to find the sum of the reciprocals of squared natural numbers? We now know Bernoulli determined this number had to be finite, but could not figure out exactly what the sum was, only that it was less than 2. In 1735, Bernoulli's pupil, Euler, took on this challenge, and his triumph put him on the map. At first, he attacked the series using brute force and carried the sum to 20 decimal places, an impressive feat given the lack of technology at the time. He found the sum was tending to 1.6449, meaning he would have had to sum at least 30,000 terms to recognize this. To derive the formula, Euler needed 2 tools, one being the sine function. There are 2 important facts that will be useful. One is the zeros of the sine function are located at x equals 0, plus or minus pi, plus or minus 2 pi, and so on. The second fact is that sine of x is equivalent to the Taylor series of the form. Euler used the above equation to represent y equals sine of x as an infinitely long polynomial. In the images to the right, you can see how the polynomial becomes a closer match to sine of x the more terms that are added. The other tool comes from the properties of finite polynomials. Given the following equation of p of x, we can recognize that the zeros of p of x occur at values a, b, c, d, and so on. But we can also recognize that p of 0 equals 1, since all factors would simplify to 1 when x equals 0. The book gave us an example of a cubic polynomial to demonstrate, but here's an example of a quartic polynomial. Notice the equation has 4 factors, making the zeros 2, 3, 4, and 5, and p of 0 is still equal to 1. This equation can then be simplified by multiplying out to put it in standard form. At this point, Euler had enough pieces to start putting the puzzle together. While the theorem is stated as such, we can use summation notation as an abbreviated way to represent the sum of reciprocal squares. Euler started with the following function f of x. This infinite polynomial has an output of 1 when x equals 0, meaning it can be factored once the roots of f of x are known. If f of x is multiplied by x over x, then the function simplifies to the following. By the Taylor expansion we looked at earlier, f of x must then be equivalent to sine of x over x. Therefore, as long as x does not equal 0, the function itself equals 0 when sine of x over x equals 0, or more simply, when sine of x equals 0. We already know from the original equation that f of 0 equals 1, but the rest of our solutions are easily recognizable as x equals plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on. Because of this, f of x can be factored into the following. Then, by multiplying pairs of factors, the equation simplifies to. If we relate this back to the original form of f of x, it produces the key equation, which is thought to be an extraordinary result since it equates an infinite sum to an infinite product. Next, Euler imagined multiplying out the infinite product on the right side and then collecting all terms having the same power of x. This would result in Now there are two infinite sums that equal each other. It is now possible to equate the like powers of x. If we take a look at the coefficients of x squared, then we see that negative 1 over 3 factorial is equal to the negative quantity of 1 over pi squared plus 1 over 4 pi squared, and so on. Using a bit of algebra, Euler determined that this simplifies to the following. And finally, multiplying both sides by pi squared, it is now shown that the sum of this series would equal pi squared over 6. In the current slide, you can see some of the other discoveries as a result of his previous formula. Although Euler did not discover this alternate formula for pi over 2, he did rediscover it based on his technique. He also used this technique for wilder series, such as the sum of even reciprocal squares, the sum of odd reciprocal squares by simply taking the difference between the prior two, the sum of reciprocals of the fourth power of natural numbers. However, he did not ever find the sum of reciprocals of odd power of natural numbers. That still remains a mystery. Euler continued this until he found the sum of reciprocals all the way up to the 26th power of natural numbers.